which is essentially a measure of a fluid's fluidity. Viscosity is a measure of a fluid's resistance to deformation, and you can think of it as the internal resistance it has to motion. So we're going to write a few notes down here so we remember that. So viscosity is a measure of a fluid's resistance to deformation. You can also think of it as the fluid's internal resistance to motion. You can kind of think of it of the friction that a fluid experiences when it's going to move. And this has implications for not only how quickly fluid will move when we're pouring it out of a beaker, for example, but also for the motion of objects through fluids. If you have a submarine traveling through water, or a boat traveling through water, or an airplane traveling through air, those are all fluids with which they're traveling through. And those fluids, depending on the viscosity, are going to exert different drag forces on the objects that are moving through them. And we can relate those drag forces to the shear force that's experienced by the bodies moving through the fluid. So shear force is defined by the calculation F is equal to tau times A, where F is our shear force, A is the surface area in contact between our surface or our object and the fluid. And tau we define as shear stress. And you'll recall from MER 210 that stress is defined as a force over an area. So if we take this equation and rearrange it, you'll see our shear stress tau is defined as the force, the shear force, divided by the surface area over which our fluid is contacting our surface. Now, how do we define shear stress? Let's think about that for a moment. Shear stress for most fluids can be directly proportional to what we call a deformation gradient. So for Newtonian fluids, our shear stress is defined as tau equal to this proportionality constant times du over dy. And we're going to define all these in just a moment here. Of course, tau is our shear stress. Mu is dynamic viscosity. And u is fluid velocity. And where this comes from is if we look at, for example, a fluid between two plates. There's our plates, like this. And we have a fluid between these two plates. Now let's say we apply a force to this top plate, that plate's going to move, and it's going to move with some velocity, right? Like in this plate. We have this top plate that's moving with some velocity. We'll just call that the velocity of the plate. And we have this bottom plate is stationary. The fluid velocity at this top plate is equal to the velocity of the plate. So we know that U in this top plate at where it interfaces with the plate, the fluid interfaces with the plate, is equal to the velocity of the plate. And we know that because we know that fluids in contact with a surface will stick to that surface. So a fluid in direct contact with a surface will stick to the surface. So then what's the velocity at the bottom here, at our stationary plate, where V is equal to 0? In this case, the velocity of our fluid is equal to 0 because our fluid sticks to the surface. The surface is not moving, so the velocity of our fluid is 0. So what happens is we end up with a velocity profile. At this stationary surface, our velocity is 0. And at this plate, the velocity of the fluid is whatever the velocity of the plate is. So we have a gradient of velocity that looks something like this. Now, if we're measuring y from the plate surface here, then that gradient is du dy. So that's where this term comes in from our expression. And the viscosity is the proportionality constant between the shear stress that's experienced and this velocity gradient, which happens to be equivalent to the rate of deformation of the fluid. So we have at this surface we have the velocity is and the fluid is equal to the velocity of the plate. At our stationary plate, the velocity is equal to